Section 19.4 is about properties of logarithms. So these are like tools that we'll need to use when we're solving logarithmic equations, exponential equations, and in calculus you'll use them to simplify a problem before you do calculus on it. So first we're going to talk about the properties of logarithms, and y equals the log base a of x. So this subscript here is called the base, so when you write it in exponential form, it's still the base. And now the y is the exponent, and a to the power of y equals x. So if you're interested in notation, this is the notation that means the same thing as if and only if. It's like a two-directional statement where it's true both ways. So let's use this to show that the log in any base of 1 has to be 0. And so when I'm trying to figure out problems like this, I say to myself, because a to the 0 is 1, that's how I know the log base a for any base of the number 1 is 0. And then the log base a of a is going to be 1, because a to the 1 equals a. So those are some handy little factoids that sometimes will help you simplify things. Okay, and now we're going to talk about some more properties of logarithms. And notice how it's spelled. It's different than the kind of rhythm if you're talking about musical instruments and making rhythms. It's similar to the word algorithm, which is a sequence of steps, a procedure. So in the properties that we're going to see now, we need to know that capital M and A are positive real numbers, so they're strictly greater than 0. A can't be 1, and R is any real number. So the number log base A of M is an exponent that if you take A to that power, you get back capital M. So this is another pair of inverse functions where if I do the logarithm and then I exponentiate, those two undo each other and I get back to M. And the logarithm with base a of a raised to any power equals the power. So this is the same two functions that are inverses, but in the opposite order. If we exponentiate and then do the logarithm, we get back to the number r that we started with. So let's do some specific examples. If you have 7 to the power of log base 7 of x plus 1, that's going to be x plus 1. And if I have log base 5 of 5 to the x minus 3, that's going to be x minus 3. And then we have some more useful properties of logarithms. And again, capital M and now also capital N are positive real numbers, and A is positive and A can't be 1. But then R is any one. So the log of a product equals the sum of the logs. So if I have a product inside a logarithm, that says I can rewrite it as 2 separate logs of each of the factors. Now recall that this equals means this goes both directions. It can be used to take apart a log of a product, but it can also be used to put together a sum of logs. So when we go left to right, we call that expand. And then when we go right to left, we call that compress or condense. This is those words used. Okay, then the log of a quotient says if I have a quotient as the argument of the logarithm, I can rewrite it as 2 separate logarithms with a minus in between. And again, if we use this left to right, we say we're expanding. And right to left, we're compressing. or condensing. So when we go left to right, that's something we're going to use in calculus. We do it here for practice, but we don't actually do anything with that skill. But you do need it. So remember it for about 2 years till you actually need it. And then when we go from right to left, we will use that for solving log equations. So we will use that skill. Okay, then the third one, also super useful, says if I have something that's called capital M and it has a power of R, the R can come down in the front and now be multiplying the log base A at the end. This only works if the exponent is on everything inside the logarithm. Okay, and then the R, ln A can be written as A to the R, because then we would have E to the ln of A to the R, and the E and the ln will come E. Okay, so let's now write a logarithmic expression as the sum of difference of logarithms. So most people abbreviate the word logarithms to log. So use the properties of log to rewrite log expressions. And if we rewrite a single log as the sum of difference of log, we say we are expanding the logarithm. And in the opposite path, to rewrite an expression with more than one log as an expression with a single log, that's useful for different things. So expanding is useful in calculus to simplify, and compression is useful in solving log equations. So here's some practice problems. So we can see we have a product in here. So we can write this as the ln of x squared plus the ln of the square root of 1 minus x. Now you want to rewrite radicals with powers because we've learned some properties that have powers in them. If we can rewrite our expression to have a power in it, then we can simplify it by having the exponents come down in the front. So I'll have 2 times the ln of x plus 1 half times the ln of 1 minus x. So in calculus, this given term would be horrible to try and do calculus with, and this rewrite, so easy. Okay, so then this next one, we have a quotient, so we're going to write it as the log of the numerator minus the log of the denominator. And I like to put parentheses around the argument of the logarithm. But you see how it's not really clear if I write this, whether the minus 1 is part of the logarithm or not. So this is unclear, and unclear is just generally a bad idea. Nothing to be really. So we can rewrite this cube root as 2 to 1/3 power, and then do one more step of putting the power down in the front. And now we have something that is still making good to be typed. Okay, then this is going the other direction. Now, the property of logarithms that says the log base A of n equals log base A of n plus log base A of n. Notice there are no multipliers. So we can't use this property with this 2 multiplying at the front. We need to use the power property backwards and use it to put the 2 back up on the u as an exponent. So I'll have the log base 3 of u squared minus the log base 3 of u And now I can use that quotient property to say if I have a difference of 2 logarithms, I can rewrite that as a log of a quotient. Okay, and then we have a similar situation with this one where we have a 2 that we need to bring up as an exponent. And then this is a difference of 2 logarithms, so it can be rewritten as a quotient. And now we have written it as a single logarithm. Okay, then these properties are more properties of logs, but they're pretty straightforward because I'm pretty sure you wouldn't have a hard time believing that if I have the log of one thing and the log of another thing and they're equal, their argument must also be equal. So this is just stating this as a fact. So another thing we need to be sure and address is talking about logarithms where the base is not 10 or e. So in the calculator, the only buttons we have are for finding common logarithms, which is base 10, and natural logarithms, which is base e. So this is called the change of base formula. And it says if you want to find the log in some unusual base of some number m, you can do the log with a base we know, for instance, base 10 that we can do on our calculator of the m, and then you divide it by the log of the base. And you can also use the natural log instead. These are the 2 buttons you have on the calculator. So if I want to find out what the log base 5 of 18 is, it's going to be exactly the ln of 18 over the ln of 5. But then we're going to want a decimal approximation of that. The whole point of changing the base is so that it's something that is on my calculator, and I'm going to just get about 1.796. To make sure you can get that answer on the calculator. So this next example, I would have this equals the log of 8 over the log of the square root of 5. And I'm demonstrating that I can either use the LOD, which is 10, or the LN, natural log. And I get the close answer either way. So this looks like about 2.58. Okay, so that's it.